All right, now we want to talk about the wave speed, the speed of the pulse. And we're only talking about strings. All right, so we want to see what can change the wave speed. Is it the amplitude, the frequency, the tension, or what? Okay, and again, this is only for strings. So we're going to do a simulation. All right. Oops, we're not all right. Come on. There you go. All right. Okay, so we have a small amplitude. Oh, hold on. Okay, so we have a small amplitude. This is the period, but it's related to the frequency. Low tension. Okay, so we want to see what's going to happen. All right, here we go. Oh my gosh, how can you be so slow? All right, so this is pathetic. So what we want to do is we want to see if maybe the amplitude, if we increase the amplitude, if that will change the speed. Now, we should really have a stopwatch so we can time how long it takes to go from here to here, but I'm not going to bother. We'll just do our best. All right, so I'm going to make the amplitude really big. Okay, ready? Here we go. All right, so it's a big amplitude, but what's the speed of the wave pulse? Oh my goodness, it's still super slow, right? Still super slow. So apparently, the amplitude has nothing to do with it. All right, let's change the frequency. Let's make it as high as it can go on this simulation. Oh, sorry, I didn't. Other way around. Here, hold on, sorry. Wait. Okay, so I changed the frequency, and what do you notice? Super slow still. Let me change the frequency the other direction. Okay, let's make it pulse. Oh, golly. All right, what do you notice about the speed of the wave? Super slow. All right, so frequency doesn't seem to matter. All right, so let's change the tension. Okay, I'm going to put this back to the middle. Whatever. Let's change the tension. High tension. You ready? What do you say? That's it. All right, so it's the tension. The tension plays a big role for the wave speed. The tension. Now, here's a formula. What did you do that for? Here's a formula. Oh, come on. Okay, this is a formula that's derived in the book. I'm not going to bother with it, but, I'm not going to derive it. This is the speed of the wave speed. Notice what it depends on. It depends on the tension and the linear density. The linear density is mass per unit length. So, like in chemistry, you learn mass over volume, right? Okay, well, we're talking about a string. So we're basically saying that, the volume is basically the length. So we're saying that the linear density, right? Linear density, which they call mu, is the mass per length. Okay? So that means if you have a really super dense rope, like one of these made out of, metal or something like that, this is going to be a large number, so this will be a smaller number. Okay? So the velocity of the wave speed, v string, that's what we're talking about. V string only depends on the tension and the linear density. Now that's important, and you'll see why. Okay, so let's say I have a wave, a string wave. So there's a doorknob there, and let's say there's a doorknob here, and I'm just going to pluck it to get a wave going. Well, you know, so the tension, you know, we set up tension at the beginning. So that's a property of the medium. The string that you choose, you know, it has a certain linear density. That's a property of the medium. But what we're saying is that, you know, I could just flick it a little bit. I could flick it really hard. I could get a small amplitude. I could get large amplitude. Doesn't matter. It doesn't have any effect. We just saw that, right? The amplitude has no effect. Okay, I could flick it like once every second, once every half second, once every tenth of a second. Doesn't matter. The only thing that matters with a string for the speed of the pulse is the tension and the type of string it is. So in other words, this, or these, are properties of the medium. Me, who can change the amplitude and the frequency, I am completely irrelevant. So the only things that matter for a string, for the wave speed on a string, are the properties of the medium. So you want to remember that. All right. Here is a picture of a two-dimensional wave. So you can imagine that, you know, you have a little pool of water, and you're just on top, and let's say you have no depth perception at all, right? And so if you drop a pebble, you know, you're going to see these two-dimensional waves, correct? Now, let's do the same thing, but now, you know, we're not going to be directly on top. We're going to be a little bit to the side, and we do have depth perception. So this is what we're going to see for a three-dimensional wave. So that's just for your education. All right. All right. Now, let's go back to our simulation. Now we want to discuss traveling waves in gory detail. Gory detail. Hold your horses. Stop. All right. So this is what's called a traveling wave, because it appears that the wave, well, it's not, I mean, we see the wave pulse traveling, right? In the next chapter, we'll talk about a standing wave. So this is called a traveling wave because the wave pulse is moving, it's traveling. So what we have to do now is we have to develop an equation for a traveling wave, okay? Now remember, there are two parts to a traveling wave. The displacement, which is up and down, right? The displacement of the medium for a transverse wave is up and down. But there's also the movement of the disturbance. So there's two pieces to this, right? The motion of the, again, think of this place where I took my can of spray paint and I sprayed it, right? So there's the motion of a piece of the rope, and there's the motion of the disturbance. So somehow we have to come up with one equation that accounts for both of those things. Oh gosh. All right? Because we got to do. And we will do it. All right, let's do it. All right, so first a little bit of notation. So we're just going to do the transverse wave right now because it's the easiest. And again, this is the displacement, right? This is the, you know, that's the normal position of the rope. And then we flick it, and the flip, you know, the flick or the pulse or the displacement moves to the right. So this is the displacement, this vertical distance. And for once, we're going to do something, you know, logical. So we're going to use d for the displacement. And again, right now, you know, d depends on x, right? Because there's no displacement here, 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 here. There's no displacement here. The displacement varies, right? It says there, there. So the displacement varies with position. And of course, it also varies with time. But we're just talking about position right now, all right? That's good enough for us. OK? All right, so the vertical displacement is called d as a function of x. Now, we got to get this thing, this pulse, to move to the right, right? So we got to come up with an equation where we have something moving to the right. Well, how are we going to do that? OK, so let's go back to high school algebra. OK, so here's an equation of a parabola, right? Y equals x squared. Now, how can we get this parabola to move to the right? You all know that. Well, how about this? What does that look like? Looks like this. How about this? Well, looks like this. Close enough. And so forth, right? So we're getting a parabola to move to the right, but it's moving in steps of 1. Well, we want it to move continuously, right? We want that pulse to move continuously. So what we have to look at then is, so we want to look at y equals x minus d quantity squared, all right? So that's a parabola, you know. Okay. Now, we want this thing to move to the right at a certain velocity. So, this is in meters, this is in meters, so distance, this is a d, a distance. So what's the distance in terms of the velocity and the time? Well, you know, good old physics 121, right? Distance equals speed times time. No kidding. All right, so this becomes y equals x minus vt squared, right? Now, you know, time is a continuous variable. Velocity is a constant. So what does this describe? It describes a parabola moving to the right, right? Moving to the right continuously. As time increases, this parabola keeps just moving to the right. Now, there's nothing, I mean, I just use a parabola as an example. There's nothing special about a parabola, you know. So really, this would work with any function, right? Any function at all. So basically what we're saying is that any function of x minus vt is going to move to the right in a continuous way, right? Any function, I don't care what it is. A parabola, you name it, I don't care. So, what we're saying then is that this is our equation, all right? So the displacement, which depends on position and time, equals any function of x minus vt. So any function x minus vt is going to continuously move to the right. All right? Awesome. Now, what does that describe? If this describes something moving to the right, because there's a minus sign, what does this describe? Something moving to the left. All right. So that's not a surprise, right? So there. If this is a plus, we have this thing moving to the left. And you know that from high school. All right. So here's a question for you. So which of the following equations does not describe a traveling wave? So pause, look at it carefully, and figure it out. Okay, we're back. So remember, a traveling wave has to be a function of x plus or minus vt. Well, is this a function of x plus or minus vt? Yeah. Okay, is this a function of x plus or minus vt? Yeah. Is this a function of x plus or minus vt? No, because there's an x squared, right? There's an x squared. So this is not an equation of a traveling wave. Okay, so this is the one that's not. All right, now we want to make things simple, right? So we're not going to, you know, I mean, again, this is just any old function. Well, we want to keep it nice. So we're going to use sinusoidal waves, sines and cosines. And again, as I said earlier, and as you know from your trig classes, sine and cosine are periodic in wavelength and in the period. Okay? All right. Now, for the people who took Physics 220, how do you create a sine or a cosine wave? Simple harmonic motion, right? Simple harmonic motion. If you didn't take Physics 220, don't worry about it. All right. But anyway, so what we're saying, this is like a transverse wave, right? What we're saying is that a specific piece of the rope goes up and down, right? And we want it to go like a sine or a cosine. Simple harmonic motion, okay? Okay, so what we're going to say then, oh gosh. And it doesn't matter if we use sines or cosines. It doesn't matter at all. Because, I mean, a sine is the same thing as a cosine, just shifted a little bit. So we can choose sines or cosines. And I guess I chose sine. Okay. All right, so again, we want the piece of the rope to go like this. But we want it to go like a sine or a cosine. All right? So what we're saying is that a specific piece of the rope, so that piece of the rope that I sprayed with my can of spray paint, we're saying that the displacement as a function of time, right? Just as a function of time, we want it to be a sine or a cosine. So we're saying sine omega t plus phi 0. Now, again, if you took Physics 220, this should be obvious. If you didn't, don't worry about it. Just take it for, just believe me, all right? Okay, now a couple things. This is omega. Omega is delta theta over delta t. Remember the angular velocity? And phi 0 is called the phase constant. We'll talk about it more, don't worry. Phase constant. It has to, the phase constant has to do with the position of the pulse where you start taking your data. But don't worry. Physics 220 people know what it is. Don't worry about it if you haven't taken Physics 220. All right. So this is the vertical displacement of one point of the wave. But remember, we also had dx comma t equals some function of x minus vt, right? I mean, right? All right. So what we're going to do is we're going to do a whole bunch of algebra, which I'm not going to do. If you want to see it, look in the book. But we're going to do a whole bunch of algebra, and we're going to combine these two equations. And this, oh gosh, can you see, does this show up very well with this weird color?
I can see it.
Okay.
Just choose a different color.
Yeah. Okay.
It's good.
Okay. Yellow looks pretty good?
Yeah, yellow looks good.
Yeah, okay. All right. So this results from combining these two equations and doing a bunch of algebra. So this is the displacement, which is a function of position and time. It's a sine kx minus omega t plus phi 0. And again, it's a sine. So it has to be periodic in space and in time. Now, you should be wondering about a few things. First of all, what's K? Where does K come from? What's a K, right? Well, there's a K. And, you know, this is supposed to be a function of x minus vt. What's this omega doing there? I mean, what's going on? I mean, again, it's supposed to be a function of x minus vt. I don't see a x minus vt. I see a kx minus omega t. So that's weird. Also, this is supposed to be periodic in wavelength and in period. I don't even see a wavelength. I don't even see a period. So what's going on here? So we've got to figure this stuff all out, you know? Okay, so let's look at sine. Okay, so we have sine of something. Now, in order to have a sine of something, what does the something have to be? It has to be an angle, right? It has to be an angle. Now, can't be meters. I mean, what's a sine of 3 meters? Doesn't make any sense. It can't be time. What's a sine of 2 seconds? Doesn't make any sense. So it has to be angles. Now we're going to use radians. If you forgot what that is, here's a circle. The radius r, the arc length is s, angle is theta. You hopefully learned this in high school math. S equals r theta. And this is only true if theta is in radians. So for example, 2 pi radians equals 360 degrees and all that. Okay, all right. So a radian is like 57 point something degrees. All right, so we want this to be in radians. Okay, radians. Now, come on. If I had sine x minus vt, well, this is in meters. This is in meters. Doesn't make a bit of sense, right? It doesn't work, okay? So we have to somehow convert x minus vt into radians, all right? We have to convert, since our f is sine, we have to convert this from meters into radians. Have to. So how do we do that? We do that with a k. Okay, so this is one of these little crazy things that you need to remember, right? So k equals 2 pi over lambda. It's called the wave number. It's just one of those, okay? Now what are the units? Well, 2 pi, 2 pi, that's usually radians, right? Radians over meters, right? Radians over meter. So what we're going to do is we're going to multiply this x minus vt by a k, all right? So let's do it. Let's do it piece by piece. So first let's do the first part, the x. So we have kx, right? So so kx is 2 pi over wavelength times x. Okay, whatever. Okay, so what are the units of this? Well, the 2 pi, the units, radians. So rad is short for radian. So I have a radian here. I have a meter here, right? X is in meters. I have a meter on the bottom, wavelength. So meters kill, so I get radians. Yes, that's what I want, right? That's what I want. That's cool. All right, so that's good. We did that. Now let's do the VT part. And I'm going to throw in something which I'll explain, but just keep the faith. All right. So I want a kVt. Okay, k is 2 pi over lambda. Okay, velocity. Now I want to substitute for velocity. And again, this is a periodic wave, right? So velocity is distance over time. Well, a sine wave is periodic in wavelength and in period. So let's use that. Let's use that information. So let's say that the wavelength is, let's say that the distance is 1 wavelength. Well, what's the time for 1 wavelength? Well, that's the period, right? That's the definition of period. Okay? So I'm going to use the velocity is the wavelength over the period. All right, that's cool. Wavelength over period. And then I have my time, my time. Okay, now, I want to change that. Let's see, do I want to change that? Oh, no, let's see. Okay, so now you see that the wavelengths kill. All right, so that's nice. So now I just have 2 pi time over period. And look at the units. 2 pi, that's radians. T is seconds. Uppercase T is seconds. So the units are just radians. All right, so I get the radians. But wait a second, I still know how you get this omega T. All right, so sorry, if you took Physics 220, you know this. If you didn't, you're going to learn it now. What can I say? So frequency is 1 over the period. So let's say I have a grandfather's clock, and the period is 2 seconds, all right? 2 seconds. Well, the frequency is how many cycles per second. So if the period is 2 seconds, then how many cycles per second? A half, right? A half. Okay, so you have to know this, all right? Frequency is 1 over the period. Okay, here's something else you need to know, which we learned in 220. So there's something called angular frequency. Angular frequency. Now angles, kind of thinks about radians, right? So angular frequency, this is just a definition. It's 2 pi f. So sorry guys, if you didn't take 220, you need to know this. Frequency is 1 over the period. Angular frequency is 2 pi f. So whenever they talk about frequency in a homework problem or a test or something like that, if they just say frequency, it's f. If they say angular frequency, it's omega, which is 2 pi f. And you got to get them straight, right? Okay. All right. So 2 pi little t over big T is 2 pi little t times f, right? Because 1 over t is f. And then I have a 2 pi f, that's omega. So I have omega t. Woohoo! All right? So I just multiplied this x minus vt by the k, and I got this. I got the units right, radians, and I have a kx minus omega t. And again, this phi 0 just has to do when you start taking data. Don't worry about it now. All right, so that's awesome. Okay, that's totally awesome. Okay, so now the displacement equation, you know, this is radians, this is radians, this is radians. So this is perfect. It's perfect. Okay. Now, let's see. So if I feel like it, you know, I can substitute in for k and omega, and I'll get this. All right? Right? I mean, I showed you this. I already showed you this. So this is one way to write it. Not very many things to write. But if I want to, I can put k, 2 pi over lambda. I can put omega, right? So omega, okay, let's do it. Omega is 2 pi f, which is 2 pi over t, right? Because f is 1 over t. So all I did is I substitute for k, substitute for omega, and there you go. So if you want to, you can also use this equation for the displacement. And this is kind of nice because, you know, here you have to say, well, I don't know what the wavelength is because I have to do some thinking, you know. Here, what's the period? I don't know. I have to do some thinking. Here, that's the wavelength. That's the period, you know, so it's kind of obvious. So either way, but to tell the truth, we'll use this one most of the time. But you can use that one, you know, whatever you like. Okay? All right. Here's a question for you. Which of the following equations does not describe a traveling wave? So pause your video and figure it out. Okay, we're back. So remember, a traveling wave, what did we just figure out? We said, I'll show you. The form of a traveling wave is kx minus omega t plus phi 0, or this. So, all right? So this is just a general traveling wave. So, okay, this is kx squared minus omega t squared. Is that the right form? No. Here, is it a function of kx minus omega t? Yes. Is this a function of kx minus omega t? Yes. I mean, it's some crazy function, right? This is a log, this is inverse sine, and we square it, 1 over squared. We cube it, but I don't care. This is a function of kx minus omega t. This is a function of kx minus omega t. This is not a function of kx minus omega t. So which is the one that does not describe a traveling wave? The first one, because it's not a function of kx minus omega t. Okay, I already did that. Well, we'll do it again. So I want to show you two equations. I already showed you one, but I didn't show you this one. So we're going to use these equations all the time with waves. So the one I'm going to show you now, I always call like the F equals ma of waves. I mean, it's just, you see it all the time. So that's the equation, but I want to show how you get it. Okay, so velocity again is the change in distance over the change in time. And again, you know, let's just pick a specific time, the period. What's the change in distance? A wavelength. Okay, but what's 1 over the period? It's the frequency. All right, so there you go, right? So V equals F lambda or lambda F, whatever, I don't care. So honestly, I mean, nobody likes memorizing equations, but I would memorize that. You just use it all the time, all the time. Okay, and let's see. And here's another one Okay, so velocity, so here, let's use that. V equals F lambda. And then the frequency is just omega over 2 pi, right? That's just definition, you know. And the lambda is 2 pi over k, just definition of k, right? All right, so the 2 pi's kill, and you get omega over k. And you say, why do I care? Well, you know, if you have an equation written in terms of that, you know, you can just read off the k, you just read off the omega, so then you know the speed of the wave. So that's kind of cool. So these are just equations you're going to use. That's all. Only reason I'm showing you them. All right, but don't forget. So this v here, these two v's, that's true for any wave you want, any kind of wave. However, don't forget, for a string wave, this is also true, right? The string wave, the speed is the tension over the linear density, square root of, right? So this is a specific case just for a string. All right, we'll stop there. Yeah.